Next example of the law of conservation of angular momentum. The case of a ballet dancer. A ballet dancer, when she folds her hands and dances on one leg, then what happens? Moment of inertia decreases. So what happens when a ballet dancer dances? She folds her hands and she dances on one leg. Then moment of inertia decreases because the distance decreases from the axis of rotation. Since moment of inertia is mr square, it decreases. Moment of inertia decreases. According to the law of conservation of angular momentum, what will happen to angular speed of rotation? It will increase. So she turns very fast. She turns very fast when she dances on one leg. You must have seen ballet dance also. And when she stretches her arms, then what happens? When she stretches her arms, the distance increases. Moment of inertia increases and angular speed of rotation decreases. So in order to conserve angular momentum, what will happen? I and omega, they will vary inversely. So this is the case of a ballet dancer. When she dances on one leg, her speed of rotation increases, and when she stretches her arms and stretches one leg also, then I increases and angular speed of rotation decreases and she slows down. Okay, same way, third example, when a diver performs somersaults in air before landing into water, then why does he curl his body? So why does a diver perform somersaults in air before landing into water? So you must have seen curling motion, the somersaults being performed by a diver before he skips into water. So why does he perform somersaults? So the question is, why does a diver perform somersaults in air before entering the water? Before entering the water. So by curling his body, what does he do? By curling his body, he is decreasing moment of inertia and increases angular speed. He increases angular speed of rotation by doing this. So by having more angular speed of rotation, but before landing into water, before sliding into water, he again stretches his body. By stretching his body, what will happen? Moment of inertia will increase and angular speed of rotation will decrease. So gently he will slide into the water. But to gain more angular speed, he curls his body in the air. Before diving, what does he do? He performs somersaults in the air. By doing this, by curling his body, he is decreasing moment of inertia and increasing angular speed of rotation, due to which he is able to cover more distance when he enters the water. तो आप देखते हो एक साइड पे पूल के एंटर करते हैं, दूसरी साइड से निकलते हैं, तो वो स्पीड कहां से वो गेन करते हैं? By performing these somersaults. By performing these somersaults and by curling their body in the air before entering the water, these curling movements, these are called somersaults. Okay, so this is again based on the law of conservation of angular momentum. All right, these examples are clear to you. Next example. So we have done a man sitting on a rotating turntable. That was first example. Second is ballet dancer. Third is a diver perform somersaults in the air before entering the water. And another example we can have is tornado. Why is the speed of a tornado alarmingly high in the center as compared to the sides? Okay, so this is the axis of rotation and speed of tornado that is alarmingly high in the center. Then as compared to the sides. That is why everything that is swallowed by its interior, it goes in the interior of tornado. Okay, so how we can explain that? Near the center, the distance from axis of rotation will be smaller. So moment of inertia decreases there. Okay, and vice versa, angular speed of rotation will increase there. So that's why tornado is having maximum speed near the center. A tornado is having maximum speed near its center. That's why everything is swallowed by its interior. So you can write this conceptual also. The speed of a tornado is alarmingly high in the center. Why? So this is the reason. It is alarmingly high in the center because of this reason. Is that okay? Next example. What will happen to duration of Earth? Duration of day on Earth if ice on its polar caps will melt. If the ice on polar caps of Earth melts, what will happen to duration of the day? So how can we explain that? Ice is accumulated near the poles, right? So right now moment of inertia is very small, but if it will melt, if ice will melt, the distance will decrease, moment of inertia will increase, the distance will increase, sorry, and because of that moment of inertia will also increase. From the law of conservation of angular momentum, angular speed of rotation will decrease. Now omega decreases and it is inversely proportional to time period, duration of the day. Okay, so if omega is decreasing, time period is increasing. So duration of the day will increase further. Duration of the day will increase if ice on the polar caps of Earth melts. Is that clear? So if the ice melts, R will increase, moment of inertia will increase, omega will decrease. Omega decreases, time period increases. All right. So this logic is also clear to you. All right. Sixth example. Next example is how we can identify a hard-boiled egg and a raw egg by spinning them on a tabletop. We have two eggs, one is hard-boiled, another is a raw egg. Okay. By spinning them on a tabletop, how we can distinguish between the two eggs? कौन सा hard-boiled है और कौन सा raw egg है? कैसे हम distinguish कर सकते हैं? So see, what is the logic behind? When the raw egg, it will spin, all the liquid material, it will get accumulated on its boundaries. So distance from the axis of rotation will be maximum. Distance from the axis of rotation will be more. So moment of inertia will increase, angular speed of rotation will decrease. So the egg which is spinning at a slower rate, that will be a raw boiled, that will be a raw egg. And the egg which is spinning faster must be a hard boiled egg. So on the basis of law of conservation of angular momentum, again we can distinguish between the two eggs. So these types of conceptual questions will be there. Okay, so the law of conservation of angular momentum is clear to you. Any doubt regarding this? You can find similar examples in the books. All right. Any doubt you can come up? Very interesting, all these examples, maybe in the form of questions also, and these are the applications of law of conservation of angular momentum also. Fine, is that clear? Now we are going to draw a table showing moments of inertia of different objects. So yesterday we defined moment of inertia. There is one more related term, radius of gyration. So let us define that. Then I will be telling you the moment of inertia of different objects without derivations. We are just to note down their values. What is radius of gyration? It is denoted by symbol K. How do we define this? This is the distance of center of mass from the axis of rotation. So we have a rigid body, and suppose this is center of mass of the object, this is axis of rotation. Okay, then the distance of center of mass, distance of that representative from the axis of rotation will be called radius of gyration. It is also defined as root mean square distance of all the particles from the axis of rotation, because the rigid body is composed of a number of particles. Okay, you write first definition first. Write down radius of gyration. It is the distance of center of mass. It is the distance of center of mass of a rigid body from the axis of rotation. So we can write moment of inertia of this object as mk square. We can write moment of inertia of this object according to this definition as mk square, where m is the mass of, that is concentrated at the center of mass, and k is its distance from the axis of rotation. Now write the second definition. According to this, it is root mean square distance, RMS distance. Full form of RMS is root mean square. So radius of gyration is also defined as root mean square distance of all the particles from the axis of rotation. So let us see how we can write. Suppose this is our M1 particle at a distance R1. This is our M2 particle at a distance R2 from the axis of rotation, so on. This is our nth particle with the distance Rn from the axis of rotation. So how can I write moment of inertia in terms of this? How can I write? I can write moment of inertia first particle. Yesterday also I told you. Second particle, so on up to nth particle. Or simply we can say it is summation I varying from 1 to n, okay, mi square. In summation form we could have written this also. Let us equate both the equations. Let us equate both the equations. Mk square is m1 r1 square, m2 r2 square, so on up to mn rn square. All right. If we take the masses to be the same, take out m then and multiply and divide right hand side by n, number of particles. Multiply and divide right hand side by n, the number of particles. Now what is this mn? That is total mass of the body. So it gets cancelled on both sides. That is total mass of the body. So gets cancelled on both the sides. So we get the formula of radius of gyration. Yes, it is root of, under root of, squares of, mean of their squares. So that is why it is called root mean square distance of all the particles from the axis of rotation. So there are two definitions, whichever is suitable you can write. So it is root mean square distance of all the particles from the axis of rotation. So we have taken the root of, average of, mean of their squares, squares of distances of particles. So we are getting the radius of gyration. So since this is radius, its unit will be meter. Its unit is meter. Okay. So let us write moments of inertia of different objects. And one thing you must note down, that moments of inertia of hollow bodies, they are more than solid ones. Hollow objects ka moment of inertia, that will be greater in comparison to moment of inertia of solid objects. I give you one example. Suppose you have a ring that is hollow from inside. It will have more moment of inertia as compared to a disc. Disc is a solid figure, okay, and as compared to a solid sphere, a hollow sphere will be having a greater moment of inertia. What is the reason? Because in case of hollow objects, the matter is concentrated at maximum distance from the axis of rotation. Okay, but if the object is solid one, for example, we are having disk where mass is uniformly distributed. This is the axis of rotation, so you can have somewhere average distance. So then the distance becomes less, so moment of inertia reduces. In case of hollow objects like ring or hollow cylinder or hollow sphere, there the distance is maximum because matter is here. So this distance is more. So moment of inertia of hollow objects, that is always greater than the solid counterparts. All right, so let us draw the table. So first of all, body or shape and its moment of inertia. First is ring. Moment of inertia of a ring is mr square. And of a disk, as I told you, is smaller, half mr square. Ring has more moment of inertia as compared to disk. Third is a hollow cylinder. Same as that of a ring, because you can assume a hollow cylinder to be a combination of a number of rings kept one over the other. Okay, अगर आप एक hollow cylinder में से portions cut करते हो तो these are nothing but rings. So same as that of ring. And solid cylinder, same as that of disk, because when you cut portions from solid cylinder, then you get disks. So its moment of inertia is same as that of a disk. Hollow sphere, 2 by 3 mr square. Solid sphere, 2 by 5 mr square. 2 by 5 mr square. One more, we are having uniform rod. A uniform rod. Uniform rod, about which axis? This is very important. We are writing moment of inertia about which axis? We are writing all these values for an axis passing through center of gravity and perpendicular to the plane of these objects. So for uniform rod, it is 1 by 12 ml square. For uniform rod, it is 1 by 12 ml square. Okay, clear? So you have to learn all these values. So this is, for example, moment of inertia about a ring. I am drawing the ring like this because I am taking it perpendicular to the plane of board. I am taking it perpendicular to the plane of board. So this moment of inertia I have written about an axis passing through its center and perpendicular to its plane. अगर मैं डायामीटर के अबाउट लिखना चाहूंगी तो वो डिफरेंट होगा. ठीक है, अगर इसके डायमीटर के अबाउट आई वांट टू राइट अबाउट डायमीटर, दैट विल बी हाफ mr square. I am talking about a ring, for example. About any other axis, that will be having a still different value. We used to prove all these and using two theorems, theorem of parallel and perpendicular axis, but now you have to only learn their values, and these values will be extensively used in numericals and derivations, so you can't leave these values, you have to do. Okay. So I hope you can learn this. Now let us move on towards the next article. Motion of a point mass attached to a string wound over a cylinder. Motion of a point mass attached to a string wound over a cylinder. So like this, we are having a cylinder of radius small r. A string is wound over it and a point mass is attached to the lower end, the free end of the string. We want to discuss the motion of this mass. As the string will start unwinding, the mass will start moving downwards. So we will discuss the motion of this point mass. So cylinder will rotate about this axis. So this is the axis of rotation. All right. What are the forces acting on the point mass? Weight acting in the downward direction, tension in the string. So there is tension in the string on the surface. So it will accelerate this way. So how can we write the equation? Mg minus T is equal to Ma. Say this is equation number 1. Mg minus T is equal to Ma. This is equation number 1. You know how to write the equation? Is that clear to you? All right. Now, let us see what is producing torque here. Which force is responsible for turning of this cylinder? Okay, that is obviously tension in the thread. So torque is equal to I alpha. Also, torque is equal to force into distance by definition. What is torque? Force into perpendicular distance. So the force responsible for turning is tension in the thread. Okay. And its distance is R. Equate. We get this. T and so alpha so we get the tension in terms of acceleration like this. Is this step clear to you? Yes, any problem, any doubt up till here? These are normal steps. I told you this formula accordingly. F is equal to ma, we have tau is equal to I alpha. Also torque is force into perpendicular distance. Which force is responsible for turning? Obviously not the weight. It is the tension in the thread. Into the distance. See, the thread is on the surface. So how much distance will it have from the axis of rotation? It will have r distance equal to radius of the cylinder. So also torque is equal to force into that distance, perpendicular distance, that lever arm. So equating the two, we get T, and using A is equal to R alpha, putting alpha equal to A over R, we get T equal to IA upon R square. Put this value of T now in equation number 1. Put this T in equation number 1. So what do we get? Mg minus Ia over R square is Ma. We get this equation? Okay. Find acceleration now. Take out A from here. So Mg is equal to A common. So acceleration comes out to be G 1 plus I over mr square. So this is the acceleration of that point mass, which is moving because of unturning of the thread. So this is motion of a point mass attached to a string wound over a cylinder. So learn this formula. A is equal to G over 1 plus I over mr square. Got it? Now the last article of this unit we are going to do, it's also somewhat similar, just a different kind of equation we have to form. Otherwise it is almost similar. So if this is clear to you, first of all, tell me. Any doubts? Okay, so last article, motion of a cylinder rolling down an inclined plane without slipping. So we are going to derive the condition so that a cylinder rolls down an inclined plane without slipping. Motion of a cylinder, or it can be any object. It can be any object other than cylinder also. Rolling down an inclined plane without slipping. So that it rolls, it doesn't slip, it comes down rolling. So let us draw the cross section of a cylinder. We are drawing the cross section of cylinder, it is rolling down the plane. So what forces are acting on it? Weight, mg, sin alpha, normal reaction, mg cos alpha, these are the forces acting and it is accelerating this way. Now let us see how many forces are acting in this case, and because of downward motion, force of friction is acting upwards. So there are three forces acting on the system. What are the forces that are acting? Normal reaction, force of friction and weight. Three forces are acting on the object. Let us see which force out of these three is responsible for turning motion. Which force out of the three is providing it torque? See, this normal reaction is starting from the center of gravity itself. Its torque will be zero because torque is force into distance. So it is not having any distance, it is itself lying on center of gravity. Same way mass, weight also. Weight also cannot produce a torque. But force of friction, if you see, that is having certain distance. That is having distance equal to radius of the cylinder. So in this case, turning motion, the torque is provided by force of friction. So it is responsible. Let us write the equation first. Mg sin alpha minus force of friction is equal to Ma. This is our first equation. Okay, Mg sin alpha minus force of friction is equal to Ma. Also, tau is equal to I alpha. Torque is equal to force of friction into radius, into distance. Okay, equate the two. Fr is equal to I alpha. F is equal to I alpha over R. Use A is equal to R alpha. We get IA over R square. So same way like in the previous article we got tension, we have got force of friction here. All right. Put this value of F in equation number 1. Put this value of F in equation number 1 now. We get mg sin alpha minus Ia over R square is Ma. Again you have to take out acceleration. We are to find first acceleration with which the cylinder is rolling down the plane. So after solving this, you will get this formula. A is G sine alpha 1 plus I over mr square. So last time we had the formula A is equal to G over 1 plus I over mr square. This time we are getting G sine alpha over 1 plus I over mr square. So in place of G we are having G sine alpha. Otherwise this article is similar to the previous. Is that clear? This step is clear to you? Now put in the values. We are to solve and we are to find condition of rolling without slipping also. Okay, so let us put moment of inertia for solid cylinder, if we know, is half mr square. So put I is equal to half mr square, which is the value of moment of inertia of a solid cylinder. Put I is equal to half mr square in the formula of acceleration also and in this formula of force of friction also. Put this A here, put this I here and here. So let us first find A. A will be G sine alpha 1 plus half mr square over mr square. mr square will get cancelled. We get 1 plus 1 by 2, that is 3 by 2. ऊपर जाके 2 by 3 हो जाएगा. So A is 2 by 3 G sine alpha. We get A for cylinder acceleration 2 by 3 G sine alpha. Put this value of I and A here also. What will be the force? I is half mr square. A is 2 by 3. 2 by 3 G sine alpha over R square. See what gets cancelled. We get 1 by 3 mg sine alpha. Check it whether you are getting this or not. You get 1 by 3 mg sine alpha. Are you getting this? आपका फोर्स आ रहा है इतना? कोई डाउट तो नहीं है इसमें? Okay, now from the diagram R is equal to mg cos alpha. R is mg cos alpha. Divide now. Divide both. Mg gets cancelled. What is F over R? That is mu. What is sine over cos? Tan. So 1/3 of tan alpha. This is the condition for rolling without slipping, that mu should at least be equal to 1/3 of tan of angle of inclination. Then the cylinder will roll without slipping. Otherwise not. Otherwise it won't. Okay, so what is the condition for rolling without slipping? We can convert it into inequality. That at least the coefficient of friction should be 1/3 of tangent of angle of inclination. 1/3 of tangent of angle of inclination. Is that clear, students? So now our unit is over. जो कुछ बीच में से conceptuals बनते हैं वो हम साथ साथ कर लेंगे एक्सरसाइज के साथ साथ. So sit with your NCERT tomorrow. ठीक है, तो वो हम कुछ साथ में एक्सरसाइज करते रहेंगे एंड साइड बाय साइड वी विल बी रिवाइज.